Hello! This lecture is about programs, or perhaps programming, and the act thereon of creating programs. The history of programming has yet to be written properly, I think, but two characters who are certainly mentioned in literature and thought to be important in the development of programming are Ada Lovelace, shown here, and Konrad Zuse, shown on the bottom left of the screen. Now, Lovelace had a rather complex relationship with automatic computing and programming, which is illustrated here by this relationship. This man on the left, Charles Babbage, who is well known for inventing a difference engine, which was a mechanical calculating engine, later proposed, and I think started to work on but didn't complete, something called an analytical engine, which was a programmable device, and the instructions were to be held in punched cards as used by a Jacquard loom at the time. Babbage gave a lecture in Italy, I think in Milan, arranged by Luigi Menabrea, who was an engineer but later went on to become the Prime Minister of Italy. He wrote that lecture down in French. Ada Lovelace was commissioned to translate that lecture into English, and in so doing, she added a whole series of notes about how one might practically program Babbage's machine to solve some problems in numerical analysis. So there's certainly good evidence that she sort of wrestled, if you like, with the problem of programming, thought about the steps that were necessary, and created those steps. She did not, however, create a programming language, which is the thing that I would like to talk about today. That honour probably goes to Konrad Zuse. Zuse was a German engineer who developed a series of computers imaginatively called the Z1 to the Z4, and it was the Z4 that I think was programmable, and importantly they were electronic computers, so they were more reliable than previous iterations. Zuse also thought about a language to describe programming the computers, and it was a relatively high-level language. It's a bit difficult to read nowadays. Here are two equations in that language. Each equation on a Zuse machine has 3 lines, and what the first equation says is that R0 is equal to V0 plus V1, and the second equation says that this is an increment operation. The second equation, E1.2, it says add 1 to Z2. Z2 equals Z2 plus 1. Fair enough. Now, neither of these people's ideas came to fruition. In Lovelace's case, because the analytical engine was never finished and she died early. In Zuse's case, the Z4 did get completed and was very successful, actually, but for reasons I'm not aware of, someone can post in the comment if they know, the programming language was never fully implemented. So what actually happened was in around the 1950s, programming, as it were, looked a bit like this. And what would happen was the developer, as we now call them, or programmer, would start with an algorithm. They'd work out the algorithm. They'd break it down into very low-level instructions, hence the term low-level programming. And these instructions were of the type, move the contents of this bit of memory to this bit of memory. They might not even include addition. You might have to, in some computers, you had to actually program addition. And they certainly didn't include native handling of floating point data. That all had to be, decisions were made by the program and they had to be programmed. And very often the program was entered by sort of flicking switches. So you'd say, well, I'm going to set up the first line and be this, press a button, set up the next line, and so on and so on and so on, and you did all of this. Once you'd done all of this, you then pressed a button, and the thing then sort of ran and then just stopped, and you were this was a challenge. You were left without any sort of effective way of debugging anything. So a number of people realised this was a problem. There was a British team that worked on a language called autocode, and then there was an American team of which led by Grace Hopper, who is pictured here, who started to think about what we now call as compilation. And the idea, what Hopper's idea really was, that it would be very convenient if we could write instructions to our computer in a language that was closer to the normal language of human understanding, and she would then write a program that converted that high-level language into the low-level language, and that would be then loaded into the computer and run. So that's the sort of starting point of my talk today. Let's talk about those programs and programming languages that are now in common use. Well, I don't know if Hopper knew this when she started this, but she was essentially starting a movement that would lead to hundreds and hundreds and hundreds of computer languages. So what is the history of a particular computer language? Well, that's an interesting question. There's a nice lecture by Simon Peyton Jones, who is one of the main movers behind a language called Haskell. Haskell is an example of a declarative language, a functional language. And I'll talk a bit more about those later when I get the chance. And Peyton Jones points out that most computer languages, have a sort of lifetime that looks a bit like this. They're used and developed by one graduate student, often to prove some particularly arcane, or maybe not arcane, point in computer science, and they die a quick death. Occasionally, those languages are successful, and they die an honourable death after a couple or tens of people have used them, and that's maybe somewhere between 5 and 10 years. The languages that occupy a lot of people's attention, of course, don't look like that at all. They look like this. They have this incredibly rapid growth. And amongst that, we might mention C++, Java, Perl, Ruby, C, and so on. And Peyton Jones calls this the regrettable absence of death. I think he's having a joke, really. I mean, he doesn't really mean that. But if your job is if you're interested in creating languages, and it's a very interesting intellectual exercise to create languages, it's natural enough to assume that creating more of them is a good idea. Something I don't agree with, by the way. He also points out, by the way, that most committee languages look like this. They have no users, but regrettably last for a very long time, because committees argue about what the language should be without actually using it. And he, of course, as a proponent of Haskell, was pointing out Haskell was one of a few committee languages that has had a successful life. Actually, you can measure something about language use, and there are a couple of rankings that attempt to do that. The RedMonk rankings are based largely on downloads from repositories like GitHub and so on. And then there are the TOBE rankings, which are based upon web searches, how many people are asking questions about a language. So asking questions about a language isn't super reliable, obviously, because people ask a lot of questions about, say, ML, Scheme and Haskell, because they're widely rumoured to be difficult to program in. That doesn't mean people are using them. There's a couple of effects just to point out here. Firstly, in all of these rankings, you can see a bit of a blip in 2018, and I think probably what's happening there is GitHub was bought by Microsoft, and there was a brief backlash while people moved their code around, I think, if I remember rightly. So that's probably the blip. But there's a sort of remarkable stability, really, about this. The top of the pops probably is Java, looking across these things, but is falling in popularity. which is a bit of a relief to those of us who think it's rather wordy and far too object orientated. Then comes lots of languages which are used by professional software engineers: C, C++, JavaScript, PHP and Python. And then everything else is sort of bit in the doldrums. The rapid risers are interesting. There's TypeScript, Swift, and Kotlin have got some movement to them. Kotlin is the Google recommended language now for Android, so that explains that. TypeScript is a special version of JavaScript that uses static typing, so it has the advantage of already being very close to a language that a lot of people speak, and I think it's supported by Microsoft, if I remember rightly, and Swift is supported by Apple Computer. So there's clearly some sort of commercial drive behind these languages. Now, brief interlude. What does a language look like? Okay, so I thought, no online lecture can be complete without a quiz. I mean, we're all so used to lovely quizzes. Let's have a quick look. So we've got a language here which I've called A, which has a hash include IO stream, a bit of it, and then I've labelled them B, C, D, E, F and G. So I'll give the answers at the end of a lecture. A couple of things about these examples. So they're all examples of what is called the Hello World program. And a Hello World usually with an exclamation mark, is generally regarded as the simplest program you could possibly write in a language. So if you look at program B, for example, it's delightfully simple and compact, only one line. Unlike example G here, which is nauseatingly long and tediously verbose. The time to get all of the compiler sorted, all of the integrated development downloaded, you get up your editor, type a Hello World program, hit compile and get the result. That is called the time to Hello World. And obviously if you want your language to be developed, you would like that time to Hello World to be as short as possible. To prepare this lecture I had to download and use Swift, and I think I was up and running with Swift in 20 minutes, and I also felt obliged to download and run Haskell. That wasn't so quick. Okay, it's more complicated. So time to Hello World is a sort of naive measure of that. Right, and a few quick words about development environments, which relates to the time required to do this. So this is my example of a Swift program. This is my version of Hello World. It's a bit more complicated than Hello World. It's something that computes the factorial function as well as says Hello World. Important point to realise, and this will come back in this lecture, is that nowadays there's the language and there's also the environment in which you develop the language. And a good development environment is very, very helpful to building good programs. So here, for example, we're looking at Xcode, which is the Apple Macintosh standard IDE, as it is called. And this is the program bit in the centre. And then I've trapped the output at the end here. So this program does indeed say Hello World, and it prints a number, which is I hope it is factorial 13. And then, generally speaking, and not always, programs have three components. They have something which I'm calling the preamble, which is usually some commentary and some importing some materials. In this case, it imports the foundation classes, which are, for Swift, they are a definition of what a floating point number is, how long an integer is, how characters should be encoded and all that sort of stuff, basic stuff required for the program to work on this particular computer, and it changes with computer. So that's how a language ports, to use across to various different architectures. Then it has the function definitions. These don't have to be at the beginning normally, but it's common practice to put them there. They're a bit like if you've ever seen a legal contract, they're like the definition of terms that always goes at the start of a contract. And then there's the main, or the body of the program, which is at the end, and that's usually short, so can be quite compact in modern programming style. And the idea there is you can read the main body of the program and work out what the control flow is and what's happening, and then you delve into the functions to find out really what's going on. Okay, well, this is kind of an interesting program in that it uses a function here, let me see if I can point it out, called factorial, that calls itself. Okay, well, that's a nice little bit of interest. It's called recursion. I think I might have mentioned recursion in the lecture on algorithms. So this function, let me just sort of read it for you. This says there's a function called factorial. It takes one argument, which I'm going to call n, which is an integer, and it returns an argument that is also an integer. It says if n is less than 1, then you should return 1. Otherwise, do something else. And to do something else is you should multiply factorial n minus 1 by n. So if you don't know, factorial n is n times n minus 1 times n minus 2 times n minus 3 and so on times 2 times 3 times 2 times 1. So it's a product of all of the numbers up to n. Actually, there's a bug in this program. There's lots of bugs in this program, but the most obvious one is that because factorials are enormously large, we will, for small n, probably exceed the range of an integer. In this one, I know that to be the case, actually. So proper programming practice would be to trap that, but I'm not going to bulk out the program with lots of traps. I just want to illustrate this to you now. Functions have had a very important feature in computer science over the years, and programming certainly. They're regarded as highly favourable because they are ways of modularizing the code. You can share function. You'd like to be able to share functions between developers. I have a function for doing this and you have that. And all you need to agree is the arguments to pass that properly. And functions usually use a common bit of memory for passing arguments called the stack. So when you recur, when you call a function, what happens, in this case we're calling factorial 13, we put the number 13 on the stack, which is this special bit of allocated memory somewhere. Then we go into that function, it calls itself again, and it puts 12 now on the stack, and then 11 and 10 and 9 and 8, 7, until it gets to 1. It then pops the stack, as it's called, removes those things off the stack, and then returns the value. So recursion is notorious for stack overflow problems. The stack can go very large very quickly, and so again, if this was a real program, we would have quite a lot of run code trapping to make sure that we didn't have any stack overflow errors, or indeed we would have written the function in a different way. Functions are, this is an example, to use some of the parlance of programmers, this is an example of a language that calls by value. We put the value 13 onto the stack, and then we pass that to the function, which then does its thing. Okay, well, we've segued quite neatly into programming jargon. Let's pick up some of them. Call by name, call by value. Okay, so let's call by value. That's just what we've been talking about, which was passing a number onto the stack. Call by name is interesting. There are languages that call by name. Call by name, we don't pass the value onto the stack. We pass the function itself with no obligation to evaluate it until it's actually required, usually. That's called lazy evaluation. Lazy evaluation means keep a record of what you've got to evaluate, but don't actually evaluate it until the program really, really needs a result. It can be quite tidy and attractive. Typing. I haven't talked about typing. In the previous example, you noticed I declared n to be an integer. And I had to declare that before compilation time. If I hadn't declared it to be an integer, the program would not have compiled. It would have failed. So that is a strict typing that has to happen before compilation. That's what we call statically typed language. I needn't have done it. I needn't have had a language like that. I could have a language like this, for example. This is Python, where I assign, in the language, I assign x a value 100, I assign y the value 0. So you could presume that they were integers. Might not be, but you could presume they were integers. And then y, perfectly legitimate to compute y as x divided by 3, so it would give the answer 33 and a third recurring. And y would therefore change type from being an integer to a double. Or I could, that's perfectly legitimate and legal, I could assign x to a string, Richard, that would be legal. I can't divide x by 2, that will lead to a runtime error. So that's one of the problems with dynamic languages like, say, Python. Now, whether you think static typing or dynamic typing or type inference, which is guessing the type from the right-hand side of the equation, whether you think that's a good idea is entirely a sort of psychological question. I had a friend of mine who described moving to dynamic typing. He said it's a bit like getting out of prison clothes and putting on your striped loon pants and platform heels. Well, so clearly he's a child of the 60s, but it's sort of an entertaining sort of thought. You can sort of relax. It's the modern equivalent of loungewear, dynamic typing. Whereas some people would regard dynamic typing as the sort of equivalent of drinking absinthe in a bar in the back streets of Mogadishu. It's probably bad for your health and certainly bad for your wealth. So, horses for courses. Arguments run violently as to the relative benefits of these two approaches. My attempt in this lecture is not really to judge between them. I'm not sure I'm even competent to do that, but to just bring your attention to some of these debates. Okay, so this is some attempt at a timeline of languages, and there's some exciting languages here on the list. You might notice that they sort of thin out a bit after a few years. So we start here at autocode, and this is the Hopper language, Flowmatic. Let's pick some big ones. So some of the languages we're using today have quite a history. So C is a big one. C is a sort of programmer's language and often used for interacting with hardware. It's particularly effective at that. Basic was a starting point for a lot of us. Let's pick another one. C++ is 80s. Surprisingly old people. PostScript, a language used by printers and display devices. It's a language that uses reverse Polish notation, which is fun and efficient, easier to type. What else have we got here? Python is relatively new, and these ones, it thins out a bit recently. I don't think that's because languages aren't being developed. I think it's because if you go back to the Peyton-Jones graph that I sketched earlier on, there are new languages being developed, but I just don't know about them because they haven't reached critical mass. Okay, now it's difficult to categorize languages. There is not an approved taxonomy, I'm sorry to say. If you go onto Wikipedia, I think I found 50 different categories of types of language, and some of those types cross multiple languages. So a couple of my favourites. There's a category of languages called esoteric. So one of my favourites on that was SPL, Shakespeare Programming Language, where somebody has produced a mapping from what looks to be a fairly conventional programming language to Shakespearean language. Now, some people will call that a binding. Binding is a different set of words for the standard commands in a language, and some people will call that a new language. I'm afraid I didn't check whether it was just a binding or a language, but I like the idea. You do have a look at it on Wikipedia, it's great fun. And I suppose I should also mention a rather interesting subgenre, which is HDLs, hardware description languages. This is one called VHDL. And the idea here is that you describe your hardware in a language. When you hit compile, you produce a net list, which is the description of all of the connections in your designated hardware. You run that through a simulator to check it's going to work properly. When you're happy with that, you press the button, and on your desk you plug in a programmable piece of hardware called a field programmable gate array, which is a small chip. You essentially blow links on the chip that connect various wires to each other, and you've got a custom integrated circuit. Or if you've got a couple of $100,000 to spare, you have it made at a silicon foundry, and what comes back are bits of silicon. So if you open up a typical electronic device, let's say a mobile phone or something like that, you'll find lots of ASICs in it, which were probably designed from software. And if you want the final icing on the cake, there are mappings from conventional languages to HDLs to silicon. So in previous lectures, I've pointed out that computer scientists see algorithms and the hardware as interchangeable. There's a complete interchange between mathematical functions, algorithms, and hardware. They're exactly the same thing, just expressed differently, and you see that in languages as well. So if you have a program, we can probably convert it into some sort of hardware implementation, and we might be able to do that through one of these mappings. Okay, great. Now then, let's have a quick look at these. I've been talking about one type of language up to now, which people would call imperative languages, or sometimes they're called procedural languages. And the thing about an imperative language is it describes in a set of steps very precisely and carefully what exactly should happen in each step. So this is an example of a very early imperative language. It's Flowmatic, which is one of the Grace Hopper inventions, and you can see it looks a bit like a modern language. It's got lines here. You can probably look at each line and you can say, well, line 2a says n equals n plus 1, so that's incrementing n. But what you can't do is look at that and work out what's going on. There's a lot of sort of reverse engineering to work that out. So if I gave you this problem statement, the formulae, and the flowchart, which comes from the Flowmatic manual, in fact, then it's a lot easier to work out what's going on. So one of the problems with imperative languages is they don't map particularly easily into real life. So one solution to that is to replace imperative programs with declarative programs. So I need a way to explain that neatly, and here's a little example. Let's find when it was. I think it was 1666, wasn't it? No, 21st of February 1661. According to Samuel Pepys's diaries, he was hanging out at Trinity House, which was based in Water Lane near the Thames. And that evening he went up to meet Christopher Wren at Gresham College. And at those days, Gresham College was just off Broad Street on the place now occupied by Tower 42. Fine. So I picked these two guys because they were both Gresham professors. What distinguished ancestors we have. And one way that Wren could have given the route to Pepys, assuming that Pepys, who lived just up the road, didn't know the way, which is unlikely, but bear with me, is just give him a set of instructions. So here they are, walk up Water Lane, turn left on Tower Street, turn right onto Idle Lane, turn left onto Little East Street, and so on and so on and so on. And Pepys arrived. That's imperative programming. Detailed instructions to get from one place to the other. Actually, looking at the instructions, not so easy to work out where Pepys was or where he's going to. Declarative programming is quite different. And declarative programming says, come to Gresham College. Right? And Pepys is left to work out the route. Wren doesn't worry about the route. He just knows that he's given unambiguous direction to Pepys to get there. that's exactly what happens in a declarative program. We tell the computer or compiler what it is we wish to be true, and we leave it to get the results. So declarative programming rocks up in all sorts of places. I mean, one example is languages that write compilers. Okay, they're called compilers. The most famous of these is called YAC, which stands for Yet Another Compiler, which I think is a sort of tacit admission that computer scientists were in the habit of writing too many languages and too many compilers. Haskell's another, Prolog's are and some languages can do both. I'll quickly show you how that might work. This is JavaScript. JavaScript is an interesting language. It runs on your browser. And actually it's not compiled, at least I'm pretty sure it's not compiled, it's interpreted. An interpreter is like a compiler, but it runs line by line. Okay, it doesn't. So compilation is usually a batch process. We write the program, we compile the thing, and then we run it. Interpreting runs it line by line as it comes, as it hits the interpreter. So this looks a bit sort of rebarbative, but let's just have a quick look at it. What I've done here is we've got an array of integers in this case. I've defined a function here which says square things up, so it says x equals x times x. And then this rubbish here, let I equals 1, it says for each one of these, go through, select this and square it up and put the output in Z. Right? You can see immediately the problem here, which is a very simple thing, which was just square everything in the array, has become complex and error-prone and difficult to work with. Declarative equivalent is this. Oh, there's a parentheses missing on the end there, should be there. Okay, same definition of the array. Z equals the map of v squared. Neat. Okay, so that's the advantage of the that's the great advantage of the declarative programming style. Now we have sort of segued into a rather sensitive area, which is programming style, and it's a bit like linguistic style. If you've temperatures can run rather hot, can't they, about whether you have indeed split an infinitive, or whether your apostrophes are in the right sense, or whether you should in the right place, or whether you should end a sentence in a preposition. And I would say tempers are even more frayed over good programming style. And I don't want to do this gratuitously, but it is important to realise and note that a number of very, very distinguished people have had quite a lot of vigorous things to say about the right way to write programs. So this is Edgar Dijkstra, for example. Dijkstra is famous for the paper Go-To Statement Considered Harmful, in which he points out that lots of bad programmers use too many go-tos, and in his view it would be a jolly good thing if there were no go-tos at all. A go-to is a jump from one part of a code to another part of code. He's also famous for saying programming basic causes brain damage. Teaching COBOL ought to be regarded as a criminal act. Now, I mean, I assume these were jokes. I'm not sure that Dijkstra was known for jokes, but the COBOL was a very important commercial programming language used by many, many, many organisations. So saying that teaching it was a bad idea is a pretty weird thing to say on the face of it. I can only assume it was meant as a joke, and it was meant as a criticism of COBOL rather than criticism of the teachers. But he's not alone. If we turn to Niklaus Wirth, who is pictured here and is the author of Algorithms plus Data Structures equals Programs, then he is similarly sort of trenchant about software development. I mean, he says C++ is an insult to the human brain. Now, I've got a lot of sympathy with that view. I can't bear C++ for a number of reasons that we won't go into. But these are quite sort of strong statements about essentially stylistic matters. And let me give you one more example. This is Linus Torvalds speaking here. So Linus is being asked a question by a member of the audience at a development conference. If you don't know, Linus Torvalds was the developer who single-handedly really created Linux, which is a variant of the Unix operating system built ground up by Torvalds. He's a brilliant developer. He also developed and he knows he's a difficult man. I mean, he also developed the source code control system called Git, and GIT. When he was asked why it was called Git, I mean, the first thing he said was, well, I was looking for a 3-letter word that wasn't used already in Unix. And then he humorously, I assume, said, well, I named Linux after myself and I named Git after myself. This is what he says. This is a commentary about what he said to a fellow developer.
I'm sorry to ask this question almost, but it's something that I think is a little bit important. How do you think it affects the culture of a community of a project when the leader is on that project's public mailing list telling people in response to patch reviews that they should be retroactively aborted?
Right.
And maybe that you're surprised that they're still alive because they should have starved to death when they were children because they were too stupid to find a pit to suck on.
I agree that some people might be put off by that.
Okay, I agree some people might be put off by that. Well, I'm not surprised. Now, I'm not just casting stones here. I think there's a serious point in these that follows from these comments, which I'd like to come back to once we've just considered briefly development as the structure of development, because programming isn't quite the same thing as development. And let me sort of illustrate that with a little diagram. So the whole field of developing software, dealing with the customer and the users and making decisions and so on along that, and maintaining the software and reusing the software and so on, is generally called software engineering or software development. Nestling somewhere in there is an activity called programming, which we've been talking about. Some people call it coding. Right? Then overlapping largely with that is something called development. I think people would see development as a slightly larger activity than just the business of cutting code. I mean, development also includes, I think, probably algorithm development, customer interactions, and so on. And then overlapping with that is something that I've called it DevOps. Now, I'm rather regretting calling it DevOps, because DevOps has a sort of technical meaning to do with using Agile and various other things. But what I mean by it here are the systems, processes, and above all, technical systems that are involved in good development. So they might include customer management systems, change control systems, and so on and so on and so on. So here are some of those development tools that you will use if you're building software. And this is only a small list. And each one of those, I've only put a small list of examples. Let me pick one that I think has general applicability, which is code repositories or versioning systems. Git was the one I referred to earlier, which was written by Linus Torvalds, but they all pretty much have the same function. Here's the problem. You've got 100 people in a big open source project working on some code. How do you know who is doing what? How do you make sure that Fred isn't interacting unfavourably with Anna, who's working on the same bits of code? So you have to have a central system that issues bits of code to people, allows them to submit their changes, they get reviewed. If they're successful, they get passed in, the system gets rebuilt, and you have a new version of the software. That's version control. It's very important, and it's not the same as track changes in Word. Right? Track changes in Word is getting better, but it doesn't have the discipline of a proper change control system. By the way, if you're ever working on a collaborative document like a newsletter or an anthology or something, can I just beg you to use source code control? Because it would make your life so much easier, and it's so much better for rolling back changes and all those sorts of things. These tools are needed because we're dealing with projects that look a bit like this. So this is, now if we look at this diagram, this sort of part of the diagram is pretty conventional for any engineering project. There's a customer who usually pays for the development. That customer specifies in some sort of loose way to a designer or team of designers about what it is they need. The designer formalises that specification, and I think probably this arrow should have pointed towards the developers, but they help design the program, and then there are developers who do the programming or the coding. So that's my argument for why programming is a small part of a larger whole called software engineering. There are then users stacked up over here in an unorderly queue, as users always are. There are users for the binary. The binary is the executable bit of the program, the thing that comes out of your compiler. There are also users for the source record, SRC, or the source code, and they have different needs. I mean, they want source code that they can read and integrate with their projects, right? Because they might be building libraries of software, which are illustrated over here, which are needed in order to make this program run on particular hardware. And there's loads of these. I mean, hundreds and hundreds of thousands of lines of code are sitting here in a modern operating system. And then we also have hardware dependencies over here. I've written hardware libraries. I don't know why I wrote that. Let's say hardware, right? There's tons and tons of little hardware variants, all of which have to have what are called drivers to connect them to usually something called an operating system. It doesn't have to have an operating system. And they all introduce dependencies. Now, this bit is rather dramatically different from a physical project, and that bit is, that's one of the natures of the challenges of software development. There are lots of other challenges which don't exist with physical projects. I think in the transcript I list 5, but let's just pick one. Any change that these people make here, if it is approved by these people, will be instantly propagated to potentially millions of these people around the world. Now, other engineering projects don't have that issue. There's a delayed rollout of projects. There's a scaling that gives you time to fix things. Now, you usually have to impose that in the software development life cycle, as it's called, to make sure that you are producing your software, either to, somewhere in what's called the quality triangle, So the quality triangle is meant to illustrate the trade-offs that exist in all engineering projects, but particularly software projects. You can have your project done to time, but it might not be to the quality you require. You can have it done to the quality you require, but there's going to be a cost to that, and so on. And developers usually have rather different views as to where they are on the quality triangle compared to, say, the customer. The customer obviously wants some things done as cheaply as possible. The developer tends to want things done to a higher quality as possible. Right. Okay. So far, so good. Well, not so far, so good, I think. What I've been describing is a rather peculiar situation where there is a plethora of computer languages, all of which technically have very, very similar functionalities, but take time to learn and have different user groups, and there are different sort of factions arguing for those. There are quite vigorous debates about the way you program, but there is a desperate, in my view, paucity of concrete evidence on why you should do it one way rather than another way. To give you just an example, and I don't really want to call anyone out particularly, but the Bible of practical computer science really is called The Art of Programming by Donald Knuth, who is an academic, retired academic now at, I think he's at Stanford University, and it's 5 volumes and counting, because there are add-ons that bring in the latest research. It's a great read. I mean, Bill Gates once said, if you've read The Art of Programming, if you read all of the volumes of The Art of Programming, you can send me your CV, meaning no one has really read it all. But if you want to know how to do a sort, if you want to know how to search for something, if you want to visualize how trees work, you go to Knuth's book, right? Perfect. It doesn't talk about the art of programming at all. The art of programming is what language to choose, how to work with people, what software practices to engage with, how to make your programs readable. I mean, Knuth also gave us something called literate programming, which is a very useful idea. The idea is that you should write your programs to be read by humans, not particularly to be read by computers. Fantastic, great idea. Where is the evidence that works? So that is a rather puzzling and I think regrettable situation with the art of programming at the moment, which is far too much art and not enough science. There are very few observational studies of activities associated with programming. There's a desperate need for hardcore social scientists to really measure what's happening in the software development process. Let me give you an example. I'll pick one that's quite well studied. Code reviews. Okay, it's generally regarded as good practice that everybody on the development team should have their code reviewed by an experienced programmer on the team who isn't them. Right? It's a good way to spot errors, and most importantly, it's a good way to ensure a consistent style. And the thought is that consistent programming style is easier to work with. Right. What do we know about code reviews? Okay, well, people have measured how often they happen. They've measured how they're done in Microsoft, Google, and various other big corporations. They've measured whether developers like them. Not much, but they put up with them. They've measured how long they take. But have they measured whether they reduce the number of bugs? There's some evidence, but it's not very strong. That's a bit disappointing. But the whole point of code reviews is to reduce bugs, right? I'd expect strong evidence for that. I've said here, functional and declarative languages have some promise. Great, yes, they do. What's the evidence for that? These are basically stylistic questions. There are people, of which I am one, who look at a language and say, I don't like that very much, for reasons that are rather cultural and subjective. And depending on the sort of person you are, you either find this very delightful. I mean, I work at the University of East Anglia, which has a very, very good creative writing department. So I'm quite used to listening in on stylistic discussions between authors. And I have to tell you, when I listen to those discussions, they sound very like discussions between programmers. Programs are really literary works. And that's a nice segue actually onto just observation about patent protections. Programs are indeed treated as literary works by patent offices around the world, so they're subject to copyright automatically arises. You don't need to file for it. The business of patenting computer programs has been very troublesome over the years, and there's probably a long lecture to be given, which I haven't got time to give, on the way computer programs are treated. There's a difference between the European Patent Office and the US Patent and Trademark Office on current practice. That's for sure. What is puzzling to me is that certain things are specifically excluded from patentability, of which algorithms are one, formulae are another. I think I've previously said, and I'm not the first to say this, there are many lectures, books and papers in computer science which point out that algorithms, computer programs and hardware have a complete equivalency between them. So it is most odd to find that one of those ways of expressing it is not patentable. Whether that gave rise to the open source movement, I couldn't quite tell you. Open source was really certainly some members of open source were reacting to what they saw as the absurdity and crushing of innovation that comes with patenting. equally, another part of the open source movement was really concerned with the need for you to have access to the source code. You shouldn't really be running something on your program, on your own computer, that you don't understand. That said, the open source movement has been one of the most powerful, important features of the computer science industry, and I think it's really quite remarkable to see quite astonishingly wealthy companies who have every reason to want to protect their intellectual property making quite a lot of it available for free, and they've just developed business models that allow them to do that, and that has been an incredibly important innovation. And the fact that it's working at all is some sort of evidence that my concerns about not properly measuring things are not as serious as you might, as I worry about. But I think I do return to my central point of this lecture, which is there is a need, and I hope it will arise, that we will start to measure confidently and scientifically the effects of some of these what appear to be stylistic choices on software design. Right, I think I started with a quiz. Here are your answers. Okay, so on top left we have C++. Python is notoriously compact, and that's the one on the top there. Bash is a script language used in the Unix cell. C, oh, we all love C, is on the right hand side. Fortran, one of the oldest programming languages in the world. I've used old style where it's all capitalized. I think it's still legal. Prolog, logical language, and Java, notoriously verbose, is down the bottom. If you've got all those, well done. You probably didn't need to watch the lecture. Hope you enjoyed it. Next time, we're going to be looking at the history of computers and computation. And I realised at the beginning of this lecture I forgot to thank and acknowledge the worshipful company of information technologists who sponsor this chair, the Professorship of IT at Gresham College, amongst other great things. If you're interested in what they do, please go to their website. Thank you.